Example 7.4, calculate the currents I1 and I2 two different ways, using resistor reduction and using Kirchhoff's laws. That is, set up two equations and two unknowns. What is the energy transfer of the 12 volt and 4 volt sources? Which source is active or passive? So let's color the nodes and redraw it to make it easier to, I guess, digest. So as always, let's color the nodes and redraw circuit into a nicer form. So here's the original circuit right here. And when I'm looking at the circuit, I'm gonna start picking my values here, and that's gonna be my ground right here. Now I don't know what I'm gonna label that yet until I start counting all my nodes. So I would say that this guy I'm gonna choose as A. And we could see here is that this A tells us that that's 12 volts. Then I'll go to my next node, which I'll call B. And then finally, nope, I have two more nodes. Then I'll call this node C. And then there's a node right here. Relative to the ground, I'm going to call this D. But that node relative to the ground, note that the source's opposite is minus 4 volts. So if I choose that as D, then E is in my ground. So now I'm just looking for what is in series, what is in parallel. So if I look between B and C, between the green and the blue nodes, so between nodes B and C, we see that we have a 4 ohm parallel to a 4 ohm, which then gives us 2 ohms. So now if I look at node A, you could see here that if I look at the 4 ohm here on the leftmost, that's going to be in series with the two 4 ohms, which is now a 2 ohm, and that's going to be in series with the 4 ohm. In other words, if I was to try to put this into words, I'm going to look at between. So I'm looking at a series of nodes. I'm going from the red to the green and then to the blue. So I have 4 parallel in series with 2. So then that tells me I'm going from A to B to C. And then you could see that I have a 4 ohm that's also in series. So what I'm saying is that between these nodes here, all these resistors are in series. And then just one last note, if you look at the node between A and E, note that those guys are in series. So parallel. So between nodes A and E, I could see here that the 4 ohm and 12 volt are in parallel. So I could actually change the orientation of them, and I could switch the 12 volt and the 4 ohm because they're in parallel, so it doesn't matter. So now let's redraw this circuit. So the long circuit is going to be the one where A, B, C, D. So let's start drawing that. So if I look at the circuit, I'm going to go that I'm going to come down, and now I'm going from A to B. So here's my red node right here. Now I have two resistors in parallel, and then I'm going to put that right here. So this is the 4 ohm, and you could see here is that this is A, and then the next node is B. There's B. Now I have the two 4 ohms in parallel, which we already discussed here. So this is the 4 parallel to the 4, which is now a 2 ohm. And then I hit a blue node, and then I go to a 4 ohm. So then if I continue to draw this, I have another resistor, but now I have this blue node, and I think I call this C, and then this is a 4 ohm right here. So if I'm looking at that, I have 3 resistors. So I got the 4, 2 4s in parallel, a 4, then I go to node D, and then I have the source. So now I need to come in here, and I'm going to put my source right in here. And this guy's in the opposite direction. Let me make sure I get this node in right here. So this node is what we called D. So this guy's going to come all the way to the ground, and then we're going to head off in this direction. So this source is in the opposite direction, and that's 4 volts. So if this is the ground right here, and this is what we called 0, then I know that I got this guy right here, and that's 0 volts. That forces D to be minus 4 volts. Now I can include the 12 and the 4, but I'm going to switch to 12 and the 4. And so now if I come back, I'm going to come all the way here. I'm going to go down. That's probably about the middle. And then this guy's coming all the way back down. Then I have my other resistor right here. So now I can write this as 12, oops, not 2 volts, 12 volts. And this guy is the 4 ohm. So now color coding everything again. You can see that up here, I still have my A node, which is 12 volts. And then down here, I'm going to have my ground. So what are my currents? One of this current tells me that this current right here is what we called I1. The other current that we talked about is that we're seeing a current coming down through this 4 ohm. So this current here is called I2. Now, when I look at the circuit, we could simplify quite a bit. And the reason why is that note that all of these resistors in series, so I could write it as one resistor. So now the equivalent circuit tells me that I have, I don't know, let's say that I'm going to go here. I have my source, which is going to be 12 volts. Then I have a resistor. I have a source here that now looks like this. So filling in my values, this is going to be positive, negative, negative, positive, That's 4 volts. This guy is 4 plus 2 plus 4. This is the equivalent 10 ohm. So what's important about this resistor here, the series resistance, is that the current I2 through the 4 ohm, because they're all in series, they all have the same current running through these guys. In other words, I have this current I2 that's moving here. I have this current I1 that's moving there. Again, as always, labeling things to make them nice and clean. So this is E equal to 0 volts. Here's my 12 volts right here. And then I have this node right here that we called D. So when I look at D, D is equal to minus 4 volts. And this is a 4 ohm resistor. So we want the current I1 and I2. What's special about this circuit is we know all the node voltages. I know the ground. I know A is 12. I know D is minus 4. So I'm going to say that we've been doing resistor reduction up to this point. So now we can just calculate this thing. Okay, so we want to calculate both of these currents by analyzing this circuit here. So I'm going to keep referring to this. So now, here we go. We want to calculate I1 and I2 using, is it resistor reduction? I'm going to write resistor reduction because we've used resistor reduction up to this point. So I1 is to the left of the circuit. I2 is to the right of the circuit. So let's calculate the current I1. So if I look at the left side of the circuit has the 12 volt source parallel to the 4 ohm resistor. So if I draw this out, I'm then going to have something like this. So I know that this is 12 volts. And I know that this is 4 ohms. But note, they tell us what direction the current is going. And we know here that this is 12 volts. This is ground. So when I'm looking at this guy, they're telling us that the current, we have to calculate the current in this direction, but we know that's not true. If that's the high, the current by itself cannot go from low to high. So we have to add a minus sign to let us know that it's going in the wrong direction. So then if I look at Ohm's law, we see that the current is going upstream. So I have to come in and say, okay, I1, what is it? Yes, it's the voltage across the 4 ohm divided by the 4 ohm. But I have to come in by hand and say, yep, this guy is going what? It's moving upstream. And that's why we put that minus sign. So if I look at the details, I'm going to get minus 12 volts. divided by 4 ohm. So I'm going to get a negative 3 amps for I1. Once again, I'm going to put in that minus sign. So now I know what that current is. Once again, the negative sign implies that the current flows, not really up, but it's flowing down. Maybe I should write that. The negative sign implies the actual current flows down towards the ground, not up towards the 12-volt node. That's why we have to put that minus sign. So now let's go look at this section right in here. So if I look at this section, how about if I just copy this and modify it a little bit? So now I want to calculate the current I2. So what I'll say here is that the right side of the circuit contains I2. So if I draw this out and modify it, here we are here. So now what I'm going to do is that I'm going to reconnect everything. And we only care about the 10 ohm resistor. And there's something really interesting about the circuit here is that according to voltages, I see the voltage across the 10 ohm resistor right here. In other words, when I look at this guy, I see that this guy has a positive and this guy has a node, and that's the voltage across the 10 ohm resistor. And the way we define that, that has to be the potential of A minus the potential of D. And we know what those two potentials are. So I'm just going to use the definition of Ohm's law. So if I look at the definition of Ohm's law, it says if I want the current of the 10 ohm, that has to be, which is what we called I2 in this case, that has to be the voltage across the 10 ohm, but that's just AD divided by the 10 ohm. But AD says that that has to be 12 volts minus 4 volts divided in by 10 ohms. And that's going to give me 16 divided by 10, which then gives me a current of 1.6 amps. Now we got to be a little bit more careful. This is a positive number, so I get a positive sign, and this now becomes 1.6 amps, and we're calling this I2. This tells us here that we picked the correct direction of the current I2. If we had gotten a negative sign for that current, then it would be going upstream. And that's not what we actually want. So now I need a copy of this circuit here. Huh, looks like I colored it. So I'm going to have to modify this just a little bit. But now we want to do the next one here. And now we want to calculate I1 and I2 using Kirchhoff's laws. And all it does here is it's going to show you a different way of doing this. So note that we've already simplified the circuit, and there are two loops where the currents are now the path direction. So what I'm going to say, so there are two loops in the simplified circuit where the current, which is also the loop directions, are assumed to be the same. So let's look at this. So remember, I got to modify this a little bit. So here's my circuit. And what I'm going to see here is that I want to get rid of all of the nodes that we've highlighted. Because I want to show you what do I mean by this. And so when I look at this thing, we don't need to label the nodes when we do KVL. Okay, we don't need to label them. So if I look at this thing here, here's my circuit. I'm going to call this, I'm going to change the colors of these. I'm going to call this green. I'm going to call this blue. And so what you're seeing is that I'm labeling the currents exactly the way we saw them in the problem. Okay? And so, and the reason why is because I picked these currents because they're in that same direction. So note that right here, this is a 10 ohm. So if I write these guys, this is what I'm actually seeing. I'm going to create a loop. So my path is going to go like this. My other path is going to go in the same direction like that. So now as I go along my current loop like this, that means I have to put in my polarities here. So I'm putting my plus and minus signs. So then I apply Kirchhoff's laws. So what I'm seeing here is that there are two loops and therefore there are two Kirchhoff voltage law equation, one for each loop. So let's write them down. I have loop 1. So I just focus on loop 1 only. And what I see here is that as I go around the loop, let's say that we start with the 4 ohm resistor. So if I start with the 4 ohm resistor, I see that this is going to give me the voltage across the 4 ohm resistor. I see a plus, so you could see that I'm gonna start right here. So I go up, so I see a plus minus, I come all the way around, and then I see the positive 12. But according to Ohm's law, the voltage across the 4 ohm should be 4 ohm times I1. So then I write this guy again, and it says that this is going to be 4 I1 plus 12 volts, and that has to equal to 0. Right there, this is what we call one of the Kirchhoff's equations, and we would call that equation 1 because we call that loop 1. Now, if I go to loop 2 here, I'm going to do the same thing. So let's say that I start right here. I'm going to start right here. And so I'm going to go straight down. So as I go straight down, look what I see. I see a positive first. So that's going to give me a positive voltage of the 10 ohm. I keep coming. Look what I see. I see a negative 4. So I'm going to write negative 4 volts. And then I'm going to come all the way up and I'm going to go to the negative 12 volts. So I'm going to get negative 12 volts. And then I come all the way back to my original one. And then again, I'm going to say that the voltage across the 10 ohm should be 10 times I2. So if I plug that in, I'm going to get 10 I2 minus 4 volts minus 12 volts, and that has to equal to 0. So that's my second Kirchhoff voltage law. So I have 2 equations. Now, these are very simple equations. Okay, so now we solve equations 1 and 2 for I1 and I2. So if I look at equation 1, you could see here is that this is a fairly simple equation. I'm going to take the 12 to the other side, and you're going to see here is that I1 is then going to be equal to what? Going to be equal to 12 volts, but there's a minus sign, divided by 4 ohms, which then gives us 3 amps for I1. But look, we get that minus sign. So what does that tell us? That tells us that the loop current that we said was, well, it just says that the current is going in the opposite direction, right? Once again, this tells us that the current is in the opposite direction, which is exactly what we calculated before. So now if I go to equation 2, you could see that on the left side, I have minus 4 minus 12, that's 16. If I take it to the other side, that's a positive quantity. So then I'm going to find that I have I2, and this will then be 16 volts divided by 10 ohms. And again, look at that plus sign. So if I look at this, then I'm going to get a value that then reads 1.6 amps, and that's I2, and we have a positive sign. This tells us here that the current pick is the actual direction. So we don't have to change anything. So now we're on our last part where we need to calculate the powers. So we need to calculate the powers of the 4-volt and the power of the 12-volt source. So I'm going to look at this circuit here. Look at the circuit. We have the 4-volt, and we know the direction of I2. So let's focus on the power of the 4-volt source. So focus on the 4-volt source. So when I do that, I have this guy right here. And I know this is minus, this is plus. We know that this is 4 volts. And then we calculated the current. We know that this current I2 we got as 1.6 amps. And the thing you want to pay attention here is look what happens. You could see here it enters the negative node. So what is this? This is an active source. So as we did before, I have my incline. And as I have my incline, this guy, we got to be careful here. This guy is what? This is a tricky one. This guy is at negative, and I should be careful here. This guy is at 0 volts. This height is below at negative 4 volts. So according to this is 0 is more positive. So what's happening? I have a charge. And what is that charge doing? It is moving uphill. And as it moves uphill, what does it do? It gains electrical potential energy, which again means that it's delivering energy to the system. So at what rate does it do it? We then say here that the power of the 4-volt source, we already saw that it's negative right away. And then we get the voltage of the 4-volt source times the current 2. So if I just plug in my numbers, I'm going to get 4 volts times 1.6 amps. And then I'm going to get a value that reads 6.40 watts. And this is the power of the 4 volts. Again, putting in that sign by hand, we know that that guy is active. Now, let's talk about the power of this guy, of the 12 volt. So our goal here is that we want to focus on the 12-volt source. And the way we do this here is that we got to go back and get the circuit. So I'm going to take this circuit and I'm going to modify this. And we're going to bring this guy down. So what do we know about this circuit here? The first thing that we do, we already know what the current direction is. So I'm going to get rid of this loop. We don't care about any of this stuff anymore. All we know is that right here, we have a current, and that's I2. So when I look at that current, we already said that that current was equal to what? 1.62 amps. We have now realized that this current I1 is not coming up, it's actually going down. So in other words, when I look at this current, it's coming in this direction, and we call this current I1, I think it was 3 amps. Is that correct? Yeah, it's 3 amps. So I should draw this a little bit different. Let's say that we see that this current is coming down. So this is I2, which is 1.62 amps. So what do we expect? We expect that the current, we're going to guess here, is that it's going to move towards node A. So my guess here is that it's coming this way, and this is the current of the 12 volt, which is also the current coming into the negative node. So I got to calculate the current through the 12 volts. So what am I going to do? I'm going to apply KCL at node A. So how about if I move this over here a little bit? So I'm going to apply KCL at node A to calculate the current I of the 12 volts. So if I apply that, it tells us that the current in has to be equal to the current out. So if I look at node A, the only current coming in is then going to be the current of the 12 volt source. Then I'm seeing here that we have two currents that are going out. One is then going to be I1. The other one is going to be I2. So if I put this all together here, you can see here is that I1 is now a positive current, as well as I2. And so when I calculate this number, I'm going to get a current of 4.62 amps. And this is the current of the 12 volts source. Now I know the current. So if I now know the current here, what we're really seeing here is that what kind of source is this thing? We've already said that, but we should really stress this point again. I have my source. Okay, I'm going to focus on the source. So here's my source. And the important thing is that note that this here is negative. Why is it negative? Because when I look at the current, look at the direction of the current. That current is the current of the 12 volt source. And we see here that it does what? It enters the negative node. That implies that it is also active and it is supplying energy. So you know what? I think I'm going to move this over here. So if that's the case, once again, my picture has to be the same picture as this guy. We'll have to modify this a little bit. Instead of that being negative, we have this here. So now we're switching this guy. This is not negative. This is now positive. And what's that positive value? That positive value is 12 volts. So if I come in here, I'm then going to say that now, here's my positive plate, which is yellow. This guy is then going to be my ground, which I'll call that guy. And we're going to say that this time, this is the ground right here at 0 volts right there. That's why that value is that. It's coming from the negative to the positive. So then the power of the 12 volt source is then going to be given by its voltage times its current. And we know that its voltage is 12 volts times the current, which is 4.6 amps. And if I look at this guy, this gives me a value of 55.6 watts. And this will be the power of the 12 volt source. But we have to keep including that negative sign. Again, that negative sign tells us that this is an active source and delivering power to the circuit.